Hello, my name is Blake Skinner, and I would like to talk about LiveSim, a live programming environment for hardware description languages. Now, first off, what is live programming? Live programming is developing a system as it is running. A live programming environment allows developers to see changes in, say, application logic reflected instantly or at least quickly in debugging output. Examples of live programming environments that are around today include widely used IDEs like Visual Studio and IntelliJ. These allow software developers to, say, change the application logic during a debugging session and just keep running without having to start the debugging session from the beginning. There's also learning tools like livecoder.net that some people like, and even some musical and performance art, which is kind of interesting. But for this presentation, what we're interested in is how we can use live programming to improve the RTL development process for large-scale digital architectures. The reason we're interested in this is because, as anyone who's worked in this space knows, building and running simulations take a lot of time. So much time that it has a real impact on productivity. Spending hours or even overnight compiling something, place and route if you're using FPGAs, and then just running the simulation sometimes because, it's often that the behavior you need to debug is thousands or millions of cycles into the test bench, and so it just takes a lot of time just letting those cycles run. And this means that verification and debugging for especially large-scale digital architectures, just take a lot more effort, more mental effort, more engineering effort, and this makes complex design more difficult to explore. Having worked in both hardware and software development, I can definitely say that hardware development, you often have to warp the design process around how difficult the verification and debugging is. It forces you to adopt more of a waterfall strategy. You have to fix variables like timing, especially very early in the development process. And, we really think that live programming, just being able to get information faster, being able to explore the complex designs more easily could really make a difference. So, live programming with HDLs, is it doable? Yes, even with large architectures. A goal of LiveSim is to see output updated within 2 seconds, and we demonstrate that even with an architecture like a mesh network of 256 RISC-V processors, it's doable. And we'll get into that in the evaluation. The way this is doable is by leveraging some key core mechanics that we're going to look at in more detail in this presentation. These are hot reloading and checkpointing. So hot reloading is being able to load code changes without stopping the simulation, to be able to just compile part of the design, update the simulation, and keep going. And in order to enable this, checkpointing is key, being able to save the simulation state and then load it up. And so we're going to look at how this works under the hood. But these aren't really novel features, though. There are tools that do this. What we're really looking at is how we can leverage this to create a live programming experience for the developer. So before we do that, I want to take a quick look at some specific use cases, how we imagine LiveSim could be used to improve the hardware development process. So as I've already mentioned, debugging a simulation, fast response, find the error quicker, also allowing simulations to skip initialization, not having to spend so many cycles warming up a cache, not having to run so many cycles to find the bug that you're trying to investigate, instead of being able to just initialize there. A tool that has a solid checkpointing, saving, and loading system enables this. Debugging what-if conditions, this is something that software tools like IntelliJ already enable, being able to, say, inject a branch misprediction at a given cycle, see what happens, go back to before that. Something you can do with checkpoints, and then of course a regression system. This is something that naturally follows. You can take a lot of checkpoints, copy, use them in parallel to run regular regressions as you're developing and changing the system. None of these things are completely novel, but having a tool that has a solid checkpointing and hot reloading capabilities is what enables this to be built into a hardware development environment. So, for the rest of this talk, we'll start out with an overview of LiveSim's architecture. Just a big picture, what it looks like from the user, how it works under the hood, and how it delivers this live programming experience. We'll look then at the mechanics that it's built on top of, hot reloading and checkpointing, and how you can build hardware simulations that enable that type of behavior. We'll take a look at some key evaluation metrics, some performance metrics, especially around some large-scale designs like that 256 RISC-V core mesh network, and then finally some concluding thoughts and future work. LiveSim Architecture. From the user's perspective, they're manipulating the design in a code editor. They're making changes to code, they're sending commands to the simulation, start, stop, take a checkpoint. So similar to pretty much every development environment. Now, the LiveSim application has the code, it receives the code changes, the commands, and it builds and maintains its own internal representation of the architecture. This representation consists of compiled code, test benches, the complete compiled simulation, which are executables. The compiled code is as shared libraries. We'll talk about this more later. But it manages the logic in that way, and then it has a state as well, which is, as I mentioned before, our checkpoints. And a key mechanic internally is that LiveSim manages the logic and the states separately. And any simulation can load a checkpoint, can load a different state. Register history is another key component of how a state is maintained. We'll talk about that more later as well. The big picture, the user is manipulating the application, sending this into LiveSim, and LiveSim, with its internal representation, is providing the live programming experience. Now let's take a closer look at the internal components of the LiveSim application and how a change in source code can be seamlessly integrated into a running simulation. So the user makes a change to the design, the source code, and this goes to the LiveSim application and eventually to the live parser in the form of source code change events. The live parser then takes excerpts of the source code and sends those to the live compiler, which can build those independently as shared object libraries. And it also updates the LiveSim application with the appropriate metadata, new version of this module, new version of this test bench, etc. The LiveSim application now has everything it needs to use hot reloading and checkpoint loading to integrate that newly compiled logic into the application. So now we're going to look in more detail at how hot reloading and checkpointing work, now that we see how these can be leveraged to integrate new logic into a running application. So internally, how LiveSim simulates RTL designs is by generating C++. This is a pretty standard way to simulate RTL designs. As I mentioned, we leverage shared object libraries. These are operating specific mechanisms that allow you to compile blocks of code and integrate them into a running executable. All the major operating systems support this. And so having a capability like that, it's really just a matter of structuring the simulation source code in a way that you can identify specific modules, drop them, load a new version, and keep the simulation running. It's just a matter of structuring the code well. Now, one important subtlety that we found in designing a system like this, to make it work well, was to separate the logic of the stages from the connections between them. In RTL languages like Verilog, the connections and the logic is often mixed into the same file, and in order to get LiveSim to work well, we do have to figure out how to separate the connections and figure out, is a change in the connection or is there just a change in the logic? But having that allows you to kind of isolate where the changes are and drop and load only what's necessary. So the process of doing this is not overly complex. I mean, the user interface sends, as I mentioned, source code changes. The live parser figures out where those are. The live compiler compiles it. We update the internal database, and then LiveSim can use the hot loading mechanism to update the simulation executable itself. So updating the logic is only part of what we need to do in order to deliver a live update to the simulation. We also need to update the state. And for that, we use LiveSim's checkpointing mechanism. So checkpoints represent state. They're dumped in a custom binary format. This includes all the registers in memory in the design, and the generated C++ is structured to allow this. So this isn't particularly difficult to manage if you don't change what the state looks like as you're manipulating the application. If you don't change how many registers there are or the memory layout in different parts of your architecture. But of course, sometimes you do. And in order to manage this, LiveSim needs to be aware of which version of your application, version in terms of repository versions, the state, the checkpoint that was generated corresponds to. And it needs a way, more importantly, of translating a checkpoint created for one version into to be used by another version. And in order to do this, LiveSim needs to maintain a register history, a history of what the state looks like between the different versions and how it can translate between them. So depicted here is the register transform history table that accomplishes this. This shows the transformations needed to move the state from one version of the architecture to another one. So for example, for version 1.0 to get to version 1.1, we created a register R. So if we had a checkpoint from 1.0, we would need to create that register within the checkpoint. 1.1 to 1.2, we create another register RA with a value -1. So that tells us how to get from 1.0 to 1.2. The structure it describes is tree-like and branching, similar to like a Git repository. And the main goal is to allow checkpoints from one version to be translated into and to be used by a simulation executable that was compiled with a different version. The reason this is so important, and the reason that we need that capability in order to deliver the live programming experience of being able to move around in time as you manipulate the design, is because when you change the logic, how do you know that any of the states you have are still valid? I mean, maybe it would have looked different if you had started the simulation from the beginning. The way that LiveSim addresses this is using the incremental simulation mechanism depicted here. The idea is that you do not start from the beginning, you simulate across checkpoint deltas. From our testing, around 10K cycles worked well. And you start the new simulation executable at one delta, you move it to the next one, and you compare the checkpoints, a simple memory comparison, and see if they're the same. If they are, then this delta checks out, but if they're not, then we know that you can't depend on any checkpoints after this delta because the state has diverged due to the new logic. So here, we see an example of an engineer who has made a code change at some point while they paused the simulation. And LiveSim has determined that starting from the most recent checkpoint is not okay because if you had started from one previous and moved across the delta, we got a different value. And so it determined that we have to go one checkpoint back, but all the ones in the past, it seems, have checked out. This does add a degree of uncertainty as to exactly how far in the past you would need to go when you make certain changes, but checking the deltas can be done in parallel, and the comparison is a simple memory comparison, so this is a highly optimized operation. So here, in the first graph we're looking at is an end-to-end test of the hot reloading and checkpoint loading mechanism. So this is the point from when the code is changed all the way up to when the state is updated. Now for this test, we used a mesh network of RISC-V cores arranged in a partition global address space. And we started with a size of 1 by 1 all the way up to 16 by 16 with 256 cores. And what we see here is that we did hit our 2 millisecond time. That was our goal originally. Some other important observations from this graph is that as the size of the mesh network increases exponentially, and since the processing cores that we're manipulating, these are just duplicated across the entire network, so any change to one module requires the change applied to every core in the network. Nonetheless, the time required to update the simulation does not even increase linearly. It's less than linearly. And the reason is because the time is still dominated by the time required to recompile. The code change in all these cases was still just in one place. And so even when you had to duplicate the new logic 256 times. In many cases, each of these cores contains 64 kilobytes of memory, and many of those changes required the memory state to be updated as well. But even so, doing large numbers of mem copies in parallel does not really take that much time in comparison to doing the recompiling. And even the recompiling, since it's just a code excerpt, can be done pretty quickly. And so this operation just scales very well, even when you're doing hot reloads of stages that are duplicated many times in a large architecture. This was an encouraging sign for us. Now the table here depicts the compilation speed of the generated C++ of LiveSim and Verilator. We're comparing after the C++ is generated, we just compare the compilation speed. And what we find is that LiveSim outperforms Verilator for compiling our RISC-V cores. The reason is because LiveSim generated individual modules of C++, whereas Verilator created an entire inlined large file. This test was done with Verilator 3.9. Unfortunately, we haven't had the chance to update the numbers with Verilator 4.0. But the other comparison that we want to make here is the comparison of LiveSim if you have already built the design before you're doing a hot reload. In that case, since you have incremental compilation, the compilation speed is much faster, and you consider that that really is the more common use case. That usually engineers, they're working with a design they've compiled at least once and they're just making small code changes. So having an architecture, and I know that there are other architectures that do incremental compilation, but that is pretty important when you consider the most common use case. So the final chart I want to look at is this one chart, this one graph here from the paper, which shows the overall simulation speed when you take into account compilation time. And this is important because when you look at the overall productivity of engineers when they're using the simulation, it's not just how fast the simulation is, it's how long it takes to actually get new information back, to make a code change and see it reflected. So you have cases of like very fast FPGA simulation architectures that take a really, really long time to build and place and route, and that kind of creates a trade-off that negates the really common use case we're looking at, which is debugging and verification. So here we see that when you have a backend that allows you to get, that when you can speed up compilation or when you can speed up simulation, both of these can contribute to the use case we're looking at. And that LiveSim, especially when you consider hot reload, I mean, in theory, you can get to any number of cycles in just 2 seconds, which would outperform any use case. And of course, there are certain caveats, but the point we're trying to make here is that having a live programming environment and being able to take a full look at the compilation time and the simulation time is what's needed to really increase the productivity of engineers in this use case of verification and debugging. Some final concluding thoughts I want to make is that the focus of my research and a big part of the UCSC Microarchitecture Lab is on developing better tools for large-scale digital architecture design. We think this is important because as engineers want to pursue increasingly large, complex, and heterogeneous architectures, better tools are needed to manage this complexity, and there's a lot of innovations in the software design space that can apply to hardware ones as well. Debugging and verification represent a major bottleneck. It costs a large amount of engineering resources and makes it difficult to explore more complex designs because it forces a more waterfall development approach as opposed to a more agile one that many software teams can use. This really limits the exploration of complex architectures. Of course, large companies like Intel, AMD, and NVIDIA can throw all the engineers and resources they need at these kind of things, but smaller companies and universities don't have so much, and better tools and design processes are going to be key in order to continue innovation in those areas. LiveSim is very much a work in progress, and it's one of many projects at the UCSC Microarchitecture Lab oriented towards improving the digital architecture design process. Thank you for watching this video, and I look forward to seeing you virtually at the conference.